Hello. If you recall, Unit 2 is all about the numbers associated, or the numbers that we see on the periodic table, and also numbers associated with the total count of protons and neutrons in the nucleus. And in this particular video, I want to do a specific problem, which is calculating the average atomic mass. That average atomic mass, you notice, is actually the numbers that you see in the periodic table underneath the letters. Okay, there's typically 3 or 4 numbers after the decimal, and it's very rarely a whole number. For instance, for boron, we see that a large percentage of the boron in the universe is the boron that has 5 protons and 6 neutrons, and it has an AMU, or atomic mass unit mass, of 11.009. But you notice that the average atomic mass is less. Well, that suggests that the other 20%, I'll tell you now that boron only has 2 main isotopes, but the other 19.9% is less than 11. It probably is an atomic number of 10. Let me show you how to do those calculations. And again, we are calculating for the average atomic mass. I'll do one example with boron, and we'll do 2 more examples, one simple and one harder, after we go through boron's case. If you typically title your notes, remember this is General Chemistry 1, this is Unit 2, and in particular this video we're going to calculate average atomic mass. Okay, boron. What are the numbers for boron? Well, the other isotope is B10. And remember, what does B10 mean? It has a mass number of 10, but you know that on the periodic table, boron has 5 protons, and the mass number is 10. Okay, so you could write it like this. That's one isotope. The other one is B11, and again, just like on the cover, you had 11 in the upper left corner, indicating what? The number of protons plus neutrons, and all boron atoms have 5 protons. Now here's the data. The data is, we saw that for boron 11, its mass was 11.009 AMU. Okay. For B10, it's actually 10.0129 AMU. Okay. Now, we also were given the abundance of B11, which was 80.1%. And if I tell you, or if your professor states that there are only 2 isotopes, the rest of the boron in the universe will be equal to 19.9%, right? This should equal 100. Other atoms or other elements, I want to use my terms precisely, other elements have more than 2 isotopes, maybe 3, 4, or 5 isotopes. Now the thing is, when we do our calculations, you want to convert this into a decimal. And you're going to multiply the AMU times the decimal amount, or you could call it the decimal fraction, but this is 0.199, and this is 0.801. Okay. Let me do the calculations and show you how to do the calculations, and then we'll summarize it into a nice formula. What I want to do is I'll put this in green, the average atomic mass. See, we just can't take the average of these 2 numbers because it depends how much of these 2 you have. Now, if it was 50-50, yeah, you could do a straight up average of 10.0129 and 11.009. I thought I had more digits. Why don't we change it so it has the same number of digits? So we'll round this to 3. 10.013 AMU. Okay. Okay, let me show you how to set this up. Because the abundance matters, and the more of an isotope you have, the more contribution it has to the average atomic mass. So you're going to take the atomic AMU of each isotope and multiply it by its abundance. This is called the abundance, and it could be expressed. Normally, it's expressed as a percentage, but to use it in the formula, you have to convert it into decimal. 0.199. Boy, several errors. Be careful. It goes with the 80.1. 0.801. We're going to try to do this really cleanly for the next example. But then you do it for the other isotope. 10.013 times its abundance, and use the decimal form. Okay, that equals the average atomic mass. And I could do this on a calculator without having to rewrite the intermediate values. So 11.009 times 0.801 equals. Okay, plus, I'm going to use some parentheses. 10.013 times 0.199 equals 10. How do you write this? Okay, go ahead, put equal sign. 10.8107. Man, should have rounded by now. Okay, AMU. But let's round this to, we're not going to do strict significant figures. 10.81, and then the last digit I'm going to round up to 1. And make sure you have your units, make sure you circle your answer so the grader can see it if this is for a quiz or exam. Look at the periodic table. The average atomic mass, 10.811, 10.811 AMU. Even though our most abundant boron isotope is the one that is 11.009. Okay, but again, you're taking the not really the average, but the weighted average, because it's weighted by the abundance. The more you have, the more contribution it has to the final average atomic mass. Let me set you up for another example, and this will be the simple example. For the simple example, let me give you silicon. Silicon 28, the AMU. Next, silicon also has an isotope that has a mass number of 29. Okay. Again, just make sure you're using the terminology correctly. 4.7%. And there is a third main isotope for silicon. That's silicon 30. .1%. Okay. I totally forgot that I was going to summarize the formula. Again, this is the mass in AMU times the abundance in decimal form. Okay, and you do that for each isotope, plus etc. Again, not the prettiest description of the formula, but why don't I pause, or you pause here and do this problem the same way that we did this problem for boron, and find the average atomic mass for silicon. mass for silicon. Because we're comparing it to a periodic table, my periodic table goes 3 digits typically past a decimal, and for silicon it does. So give your answer to 5 sig figs. Good. Go ahead and pause the video and show your work and circle your final answer, and unpause it to check it against my work. Okay, let me summarize again in a neater form the average atomic mass equation. Excuse me. Mass in AMU times abundance in decimal form plus, and this again is isotope 1. It doesn't matter what you chose as isotope 1, but you're going to do the same thing for isotope 2, check, or dot dot dot, plus isotope 3. I like to, once I have a general formula, I like to plug in all the numbers instead of doing this in parts, and because I want to see the overall equation with the data. Silicon 28 mass abundance in decimal. Hopefully you have something similar or exact on your paper. Be careful, 4.7% is in decimal form 0.047. 0.031. That will equal the average atomic mass. Okay. Now, some of you with larger displays or graphing calculators, you could literally just type this. I'm in the habit of doing things in parts on my calculator. So I do one operation, I press enter. The next operation, enter again. So plus. Okay, I'm going to press enter. Okay, I'm building up that mass, plus. Okay, before I press enter, we should expect something, if you look at the data up here, it shouldn't be in between the low and the high. It really should be much, much closer to the low because there's 92.2% of the smallest or the least massive isotope. So I'm expecting something above 27.97, but not too far above 27.97. Okay, enter. 28.086. 28.086 AMU. Circle. Whoops, you don't see that. Circle. Is that close? See, it's still pretty close. 28.086 is still pretty close to this number rather than this number right here. Let's take a look at silicon on the periodic table. 28.086. 28.086. That is the simple example. Let me give you the harder example. But keep this in mind, how this looks. And honestly, let me put also here average atomic mass. I want you to visualize this because in this case, this is x, solve for x. But in the next case, x is going to be somewhere within this equation. And you're going to have to figure out how to incorporate that x, and then how to solve for that x. And we are using gallium now. Okay. How can I mix things up? Gallium has two main isotopes, gallium-69 and gallium-71. The gallium-69 has an exact AMU mass of 68. I shouldn't use the word exact, but AMU mass of 68.9255. Okay, 4 digits past the decimal, so it is pretty accurate, or has a lot of sig figs. For the one that's 71, it's 70.9247. If you're wondering why this is not quite 71, or why this is not quite 69, in a previous video I discussed what exactly is an AMU and why there is a discrepancy between the AMU mass and the mass number, right? This is protons plus neutrons. But that is the actual atomic mass of that isotope. I'm not giving you this. I'm not giving you the percentages. Okay? I am giving you this. If the average, do you see how we're going to work backwards now? If the average atomic mass is, let's use this, 69.732. So my average atomic mass is known, 69.732 AMU. What is the abundance of each isotope? So I want the abundance of each isotope. This is intimidating because I actually don't see one variable, right? For normally when you want to solve an equation, you have one x, one variable. But here it looks like I have two. Okay, let me give you the hint. Then you're going to pause and write me out the equation with the data, incorporating those variables, okay, and then solving for that variable. So here's a hint. Make one of these x. Make one of these x. So I'm going to have this as x. Now, let's pretend that this gallium-69 has an abundance of, I don't know, 95%. X is not equal to 95. Remember, when you use the equation, you're changing it into a decimal. So you're using x as equal to 0.95. But you know how to get the decimal abundance if you know at least one of them. You do 1 minus 0.95. So you know that this is, for the second isotope, this would be 1 minus 0.95 equals 0.05. So instead of using y, x and y, you know x because x is actually, oh, not x, but you know there's abundance because that is 1 minus x. See, this is x already. 1 minus x. Now, well, I'm not going to even mention what to do if you have 3 isotopes and you don't know the abundance of any of them. Let's work with this one here. Because you know that, what's x plus 1 minus x? That's 1. Just like over here, if you add up all the decimal abundance, that should equal 1. Okay? Or if you add up these two, that equals 1. Okay, in decimal form. 100 in percentage form. All right, your task is to use those variables, x and 1 minus x, and those values, and stick it in here, and then calculate for x. And if you know x, then you will know the abundance of the second. Now, it doesn't matter which one you think is bigger or smaller. Okay, it doesn't matter what you put x with. Okay, everyone should be able to get the same percentages. Okay, pause the video. If I was grading this, I would grade up the setup, and then I would grade the final answer. Okay, pause the video and give it a go. Okay, we are trying to figure out the abundance of each gallium isotope. We know the average atomic mass, and that will be put in the beginning. 69.732 equals. Okay. Again, I'm asking you to put it in this form. Now, I know that some of you are very tempted to solve for x right away, and like isolate x and then put in your numbers. I think that causes a lot of careless errors. Go ahead and write out the equation, and it doesn't matter if x is within your formula and not as the final value. 68.9255 what? Times x, right? Times 70.9247 times what? Times 1 minus x. So we have parentheses within parentheses. We're going to have to distribute that term for each of these terms within the parentheses. Let's do this in parts. Okay, we know that we're not going to worry about the left side. This one obviously is 68.9255x plus. So here's the tricky part. So we take this and multiply it by 1. 70.9247. And then, oh boy, and then we plus this times negative x. So ultimately that will be a negative 70.9247x. Let me write this, because now we're going to put all the x on one side of the equation and all the non-x's on the other side. But double check my reasoning. Is that the same as this? I take this, multiply by 1, and then this times minus x, which will give me negative 70.9247x. And you add those two together. This, well, first we have to isolate x. Okay? I want to make sure that this is a positive number. So I am going to put the x's on this side over here. Okay? So this is, you may do this a different way, but I like to do it this way. 5x. And then when this comes over to the left side, this is plus 70.9247x. And then we already have this number. And then we're bringing this to the right. And you see why I did that? Because, see, this term is going to be positive, and this term will actually be positive as well. Okay. Let me take care of this. Actually, this side, negative 68.9255x plus 70.9247. So this is 1 point, don't round until the very end, x equals. Now we'll take care of this. 70.9247 minus 69.732, positive 1.1927x. You're going to divide both sides by that number here. So I already have this number saved, divided by this number. Ooh, yeah, nice. See, it makes sense because it's less than 1, right? Whoops. Makes sense. This would be 59.7%. But, oh no. I still have the answer. Oh man. 1.1927 divided by 1.9992. 0.59, and I'll go to 3 sig figs, 7. So the percentage is, okay, so that X is for gallium-69. So for gallium-69, the percent is 59.7%. And for gallium-71, see, I know now that you know that this is 100 minus this percentage, but look over here, it's the same thing, right? Well, if we convert this to percentages, it'll be 100 minus the percentage X. Okay. All right, so this is 100 minus 59.7, 40.3%. Or if we go back up here, you have X, sorry, 1 minus X equals 0.403. And we just convert those to decimal. Circle your answer. They want the abundance of each isotope. Yeah. Okay. There's the work, and there's my X, and I got those X's based on the fact that this equals 1 when I add these two together. Or if you convert them to percentages, they equal 100%. But think of it as these two has to equal 1. Just like these two equals 1 when you add them together. All right. Practice, practice, practice. You saw that I made some silly errors, but at least I caught them. But it takes a little bit of practice to make sure that you have the rhythm down.